Okay, so this figure shows you the doping, either intentional doping or unintentional doping in the CVD process. Okay, so we can provide the dopant, okay, with different dopant gases. And that's the intentional dope. Okay. But the dopant source at the surface can, there are some other auto-doping process in these architectural reactors. Okay. There are four kinds of auto-doping. Okay. The first one is from the wafer front side and also the wafer back side or edge, or other wafers or susceptors. Okay. So this will give you the doping profile underneath. Okay. Where we have these out diffusions, okay, this out diffusion will be the same as the one we have discussed before in the diffusion chapters. So we have this, you can consider we have an infinite source at the surface. So we do the integration of this Gaussian and so give you these complementary arrow functions. Okay, so this is a profile of this complementary arrow function. And also we have this auto-doping, which will be coming from this these four ways as shown in these figures. Okay, so this is the doping profile from auto-doping, and this is the back side. Okay. Now we move to this LPCVD. Okay, so from the introduction of AP, atmospheric pressure systems, we can see that at high temperatures, we have to use these horizontal configurations. Okay, so that means we can only process fewer wafers at a time. But if you try to reduce the temperatures, the deposition rate will goes down, and the throughput is again become low. Okay, so the solution is to operate at low pressures. Okay, so in that case, there'll be the mass transfer limited regime. Okay. So if you reduce the pressure from 760 torrs to 1 torr, okay, so that will be your this DG, your DG is inverse proportional to your P total. Okay, so that's the diffusion constant. Because at lower pressures, you have less molecules, so you have less collisions. So you actually can provide a longer mean-free path for your molecule to travel. Right? So at low temperature, at low pressure, your D can increase quickly. So you can increase this H quickly. Okay? But also your delta S will increase. But one is increased like 760 times, and this delta X is increased only 7 times. So the total Hg will increase by about 100 times. So we move from this Hg at 760 torr to this one at low pressures 1 torr. So move this Hg up. Okay. So in that case, your transportation is no longer the bottleneck. Okay. For those reactants to transport from gas phase to the surface, they go through these boundary layers. It's no longer your limiting parameters here. Okay, so increase this Hg. But you increase the Hg, you make your process more temperature sensitive. You see, right now this curve is like this. So along a wide range of temperature variations, your growth rate is actually very sensitive to your temperatures. Okay. So in that case, we have to control our temperature very accurately. Okay, so we not just use a bottom susceptors, those graphite susceptors with very good thermal conductivity, but right now we need a hot wall, which means the chamber is hot wall system. You can see these 4 chambers now. You have to provide this good and uniform control of your temperatures. Okay, so by removing the susceptor, you can reduce the auto-doping. And also your less gas carrier is needed. Okay, and your deposition rate may decrease. Okay, so in this case, because your transportation is not a limiting factor, so you can move your wafers 90 degrees. You can place it vertically. So you can place a lot of wafers in one time. But by doing this, you have to control all the furnace, the temperature environment very accurately compared to the APCVD. Okay? But once we reduce the pressure, okay, now your molecule will move directly along one direction without any collisions between these molecules. Now this surface, this surface profile or the shadowing effect now will become more important. Because right now it will move toward like physical vapor depositions. Okay, you can imagine that your molecule now move in one direction compared to if you high pressure they can climb and bump to each other. So it's less directional. Okay, and more enhanced technology, more advanced technologies is called plasma enhanced CVD. So we incorporate plasma. So what is a plasma? Okay, so plasma has been used for cutting and etching. Okay, it can apply to any operations. So by incorporating plasma in our CVD systems, we can increase the deposition rate without increasing the temperature of your substrate a lot. Because plasma can also provide energy to your gas, your molecules. And previously we used temperature to provide kinetic energy for your molecules. Now we can use plasma to do the same way. Okay. So once we have this plasma, we don't need to increase the temperature to a lot of higher temperatures. We can maintain a low temperature, especially for the case that if you already deposit metal on top of our substrates, okay, those metal, if you increase the temperature, then it provide some kind of annealing effect, or you may cause the metal to change the contact, resistance, or to sometimes you enhance the metal diffusion in your material. Okay, so we try to avoid that as when we talk about the back-end process. Once we finish all the metallization, everything, we try to maintain the temperature as low as possible by doing all the process. That which includes this kind of thin film deposition. Right? We try to lower the temperatures. But in order to reduce the temperature but maintain the high quality of your film, plasma enhanced CVD would be the better way to do this. Okay. So what is plasma? So plasma consists of electrons, ionized molecules, some neutral molecules, and neutral and ionized fragments or broken up molecules of this kind of fragments, and also some excited molecules and free radicals. Okay. So in this plasma, you can see that there's some ionized molecules, which means you provide energy. Some molecules begin to ionize, and some broken pieces of the molecules, some excited molecules, and free radicals. So what's free radicals? Okay, free radicals are electrically neutral species. Okay, they have incomplete bonding and extremely reactive. Okay, like these molecules here. They become very reactive, and because usually they have higher energy. So this is the figures of the chamber we used to describe this plasma enhanced CVD. So we will reduce the pressure to a certain low level, and we have gas. Of course, we have gas inlet to provide the gas. And we have top and bottom electrode, and we provide this RF source. Okay, so this RF source can be used to generate or produce this plasma. Okay, and this is the gas outlet pump. Okay, so we have the heaters. So we can heat up this susceptor or this electrodes, okay, maybe to 200 to 300 degrees C. Okay, and from those fragmentation of free radical and ion bombardment, that is the surface process. Okay, so they will combine with the deposition at the same time, but at much lower temperatures than the non-plasma system. Okay. But sometimes we need high density plasma. Okay. This high density plasma, we can try to add another independent RF source. Okay. So we have this 2.45 gigahertz microwave. Okay, so we have some magnetic coil on the side wall of this chamber. Okay, so this high density plasma, they can provide simultaneously deposition and sputtering at the same time. Okay, so you do the deposition and do the sputtering, and those sputtering will have especially higher etching rate at the corner of your film. So that will help you to planarize and fill the void, okay? To have the void-free films. Okay, so we will come to this later. Okay, so we have this high-density plasma because in the baking process, sometimes we have to fill out some holes via host. So we try to planarize this with more high-density plasma. Okay. Now we move to the physical vapor deposition, PVD. So by the name that we know is basically based on the physical process to produce the reactant species in the gas phase. So what kind of physical process? So that includes these evaporations, which will heat up the material and in very high vacuum chambers. Okay, this height is 10 to -5. Okay, so you heat up this source, use thermal or use electron beam to bombard this metal. It begins to increase the temperature to the melting point, and then it can evaporate. So we have this evaporate because it's at very low pressures. This chamber is at very low pressures. So there's no obstacles or other things if the chamber is clean. Okay, if the chamber is clean, then this molecule can directly go like a straight line to the wafers. So we have the wafers put up here. Okay. And the deposition rate is determined by this flux. Okay, we have this flux, and it's also geometric dependent. The wafer topographic profile will change this deposition rate, and also this wafer holder, how you place it. Okay. And the advantage of PVD is it provides little damages and very pure layer because you have very high vacuum. There's no other materials or defects in this chamber. Okay, but the disadvantage is it's not good for low vapor pressure metals. You know, some metals it can easily to heat out and evaporate. Some metals it takes much higher temperatures to do this, to get a good enough vapor pressures. Okay, and also low in situ cleaning and poor state coverage because all the molecules now moving in line of sight. So let's say, for example, we have a step here. Okay, so if all the molecules are moving in these directions, okay, so that's the extreme case I explained 8 hours ago. Then, because this surface, if this slope is close to 90 degrees, you have very few material deposited on the sidewall. So it gives you very poor state coverage compared to CVD. Okay. And there's also one problem is you may have the X-ray because you have this E-beam and bombard on your metal molecules, so you will have some excited electrons. When they reduce the energy, they will emit the X-ray, and those X-ray may cause some trap charge in your gate oxide. Okay, yeah, but you can use annealing to fix that. Okay, now we explain the mechanism of evaporations. Okay, so we use an ideal case as a point source to explain this. Okay, so you consider that a point source So when you do the evaporation, it goes into all directions. So we use this omega, which is a solid angle, to explain this. Okay, so 4 pi is in all directions. But now we consider upwards as only 2 pi upwards. Okay, so the total flux will be this rate divided by this angle and this r squared. So r is the distance between your wafers to your point source. Okay, so that's the 8K means these the wafers at these K positions. Okay, which has a theta K. The theta K is the same as theta I here, which is the outward flux angle. Okay, so now the deposition rate, we can divide it by this density, but also this cosine theta, because now the flux is at these directions. But our wafers, is placed on the wafer holders. If the wafer holder is flat, it's not curved, it is flat, then you have to time this cosine theta to get all the material to calculate the thickness actually of your wafers. So there's a cosine theta terms here. Okay. Now if because this is a point source, but actually you have a crucible and have a certain amount of small area that's your evaporation surface. Okay, so this small planar surface we call it AI. Okay, and so right now the theta I is here. It's between these certain directions and your wafer, between certain direction and your wafer. Again, your wafer placed at this K position with theta K angles. Okay, so right now, if you try to calculate this Fk, then you have to add a term which is a cosine theta with this n here to account for going to this direction. You have to turn to these directions. So this is a cosine theta I here. You have to times this term. Okay, and now for the growth rate on your wafers placed on this flat holder, you have times another cosine theta K, similar here. Okay. Now we know that this flux or this growth rate by this evaporation becomes angle dependent. It depends on this cosine theta I or cosine theta I with these exponential terms. Okay. Okay. So now we can do these simple calculations, right? So we have this holder point source here. Then we can calculate different positions on your substrate. This is K plus 1, K plus 2, and so on and so forth. Okay, so we have this different angle dependent. Okay, when we increase this L, this is L, from the position to the center. The center is normal to your point source, which has a shorter distance, H here. This is the shortest distance, H. Okay, so you increase this L, you increase this R, and you reduce your cosine theta K, so your deposition rate will reduce. So you can see this curve. We try to normalize to the growth rate at the center here. So here the y-axis is, we do the normalizations. We normalize to the growth rate at the center. So when we move this position, we increase this L. This is L over H. Okay, so we increase L, which means now you move the wafer from your point source, on top of point source, and move it away. So we can see the growth rate or the growth thickness continue to drop. So we normalize these two lines. One is point source, one is surface source. They'll give you the same trend of this decline of your thickness. So you can imagine that if you put your wafer right on top of your evaporation point or your crucible, then you get the highest or largest thickness of evaporation rate or growth rate. And once you move away from this point source, then your growth rate will drop quickly, right? So this gives us the idea that if we try to do this evaporation, the wafer holder, we won't choose this planar or level wafer holder. We have to choose a curved one. Okay, so like the figure shows here. We have to redesign these holders in order you put the wafers on it, and you can get a very uniform film across the wafers. So we can use this kind of spherical holders. Okay, and we can do the rotations. Okay, so in this way, if we put our source at the center of this spheric holders, okay, so this is for the ideal point source. So in this case, because this solid angle is too high, so we can get uniform wafers. These depositions. Okay, so but for the small area, which is more practical cases, we can put it here. We can put our metals or evaporation source here. Okay. And this is because we have this cosine dependence. Okay, if this cosine is equals to 0, okay, which is the normal directions, then we have cosine 0 equals to 1. So once you just move away from this center directions, now we have this cosine theta dependence, which will reduce your growth rate. Okay. So that's the ideal case for point source and small area surface source. Okay, but we can these are some other non-ideal behaviors. Okay, so the first one, figure A, is a uniform or isotropic emission from point source, and this one is an ideal cosine emissions for a smaller planar surface source. Okay. And this is non-ideal case. Okay, it's more anisotropic emissions, which give you this n larger than 1. If you have this term, which means that your area dependence, you have very strong area dependence. And on top of your source will give you the largest deposition rate. Okay, and we can use rotation. These two axis rotations. One is you can rotate by yourself. Okay, the other one you can rotate around your evaporation source. Okay, so this kind of two axis rotation can help you to reduce these non-ideal behaviors. Okay. And is the evaporation rate. There's an equation for it. Okay, and it depends on this vapor pressures. So in order to get reasonable rate, let's say 0.1 to 1 micron per minute, we have to maintain our evaporation rate 1 to 10 millitors. Okay, this is 1 millitors line here. Okay, in order to reach 1 millitorr, like you see this tungsten, you have to increase to almost 3000 degrees C. And for other metal like indium or gold, aluminum is usually less than 1000. Okay, so if we use evaporations, basically we can evaporate all kinds of metal we want. We can put it to different crucible or different tungsten bolt. We can heat up it, and they can co-evaporate at the same time. Okay, as long as you can reach the evaporation temperatures. Okay, you can find the good holders like graphite. Okay, so single element you can do that, but if you want to evaporate alloys, like for example, you have some alloy, maybe gold, germanium alloy, or what kind of different alloy or compounds, because they have maybe mixed 2 or 3 elements, they'll have different vapor pressures. Okay, so you have to separate them. Otherwise, you try to evaporate this alloy in a single crucible or tungsten bolt or something. At certain temperatures, there's only one element begin to evaporate. You have to increase even higher temperatures to have both elements to evaporate. But at that time, they will have different vapor pressures, so the evaporation rate will be different. Okay, so it's quite difficult to evaporate an alloy. Okay, and also this one we talked about this before. The evaporation gives you a very poor state coverage because all the molecular travel is like straight line. And also there's a sticking coefficient, SC. Okay, so what is sticking coefficient? Okay, if we evaporate something or this metal or something, okay, it deposits on this substrate and it stays there, and we call it sticking coefficient equals to 1. Okay, so that's the flux of reactant divided by the flux of excitant. Okay, so you evaporate or you have incoming, like say 100 gold atoms, okay, and it all stick on your wafers. Then we call it a sticking coefficient equals to 1. But if you come in 100 atoms and maybe 3% or 5% of them will continue to move to the other positions, then we say the sticking coefficient is less than 1. Okay. But sticking coefficient less than 1 will give you a better state coverage, right? From these figures, it can give you a better cover of these steps. Okay, so if you want to provide this good state coverage or have this smaller sticking coefficient, you can use some sputter process. Okay. Then those spotting process can give you smaller sticking coefficient and good state coverage. Okay. Okay, so let's move on to the sputtering. Okay. Sputtering, from the name, we can understand that we try to use some some atom to bombard the spartan target, and those target atoms can be sparked out of the original target and will fly through this plasma and reach to your substrate surface. Okay, so we can use this plasma to sputter the target. Okay, so we have our target put on our cathode electrode here, and we can flow in some argon gas, and we apply a source, DC source. So this is a DC case, DC spartan case, and this DC case will generate plasma. So we have argon plasma. And this argon plasma also has some glow discharge. So you can see this color. Different gas provide different color. I think, remember argon is a little bit purple? I don't remember. I think it's purple or pink. Okay. So you can by watching through this chamber window, then you know, okay, there's a plasma inside. Okay. So in this target, we can put some metal. Okay. So once we have these alloys, metals, then okay, we apply this, so argon will bombard this and sparking out some metal, and metal will come to this your surface. Okay, so compare with your evaporation method, this spartan will give you higher pressures, like 1 to 100 millitors. Okay. And this plasma contains equal number of positive argon ions and electrons, as well as neutron argon atoms. Okay, so that's, put this 90 degrees directions. So in the cathode we have the target, and here is the anode. Okay. So it's quite similar to PCVD. So we have the argon, this argon ion, they are accelerated across this cathode thief. Okay, the thief is the, I don't know how to say that. It's a dark area. Okay, it's a dark area. So we have cathode thief, anode thief. Which in this area we don't have any because of depletion of some active ions. So we won't see any glow here, no color here. Okay, so that argon will strike this target, these electrodes, and sparking out, let's say, maybe aluminum, and we have argon. Okay, and here, because it's like a depletion region, so most of the voltage drop. Okay, if you apply this voltage, we have a voltage drop across these regions, and also at these anode thief regions. Okay, and these atoms, aluminum atoms, will travel through the plasma and deposit on top of your wafers here. Okay, so here just some figures to show you that we have this argon, okay, this spartan and aluminum. So we have aluminum coming down and deposit on top of the wafer surface. And because the sticking coefficient is less than 1, so aluminum might move to other positions, other than staying at the original position. The rate of sputtering depends on the sputtering yield, Y. Okay, so Y defines the number of atoms or molecules ejected from the target per incident ion. Okay, this sputtering yield is a function of energy and your mass of ions, and also the target materials, and also the angle, incident angle. Okay. And also, you have argon sputtering here, and you have some electrons coming out because you have this area, this chamber is not at very low pressures, so you still have some oxygen here. They will move. You have some oxygen ion here, and you have this argon radical. They can continue to give out the energy and become these electrons and also the argon ion. Okay. Okay, so again we begin from this point source. Okay, when you sputter this target, okay, your target atoms can actually go to different directions. Okay, so if you have a wider or larger area of your source, then we have different arriving angles. Okay, compared with this point source. Okay, so if we have different, these arriving angles, then we will provide a more uniform coverage. Okay, in terms of coverage and thickness. So usually we will have the spotting target. We want it as large as possible to provide a wide range of arrival angles. Okay. And these middle two figures showing this anisotropic and anisotropic flux arise angle. Okay. Like for this one is isotropic flux arrival, and this one is anisotropic. Usually you have more cosine theta dependence, then there's more focus on this arriving angles. Okay, so this arrived angle distribution generally described by these terms, these cosine theta terms. Okay. Okay, so for the DC spotters, your target electrodes has to be conducting like metal, like aluminum and tungsten, right? But if you want to spot the dielectric materials, we have to use RF power source. Okay. Then when we switch this RF power, okay, because the mobility between your ions and electrons, okay, there's quite different. So that will create this kind of electrical field. And you can have this plasma between these two electrodes. Okay, so generally you have this kind of profile, okay, for this equal area electrode. Okay, so in order to, if you see these figures, okay, now you know that your argon can actually bombard this target electrode and also your wafer electrode. Okay, if things you have the same bias on both sides. Okay, so we don't want this to happen. Okay, we want our argon ion how can we do that? Okay, so we can change the area because it has an area dependence. You have inverse proportional to these areas. So we can reduce this top electrode. Okay, reduce the area. Okay, so by reducing the area, now your voltage drop will now lies in this close to this smaller area target. So now we change the profile into this dash line, and this dash line is the same as the DC what we see here in the DC spotter. Okay, so for the IF spotter, we need to have a smaller target electrode so that we can have our argon all spotting on this target instead of spotting on your wafer. Okay. And for the wafer electrode, we can also connect it to the chamber walls. Okay, so to make it like an even larger area. So by doing so, we can further increase this ratio between this V2 and V1. Okay, so increase the area ratio, we can change this voltage ratio. Okay. All right. Should we take 5 minutes break, or you want to continue? Anyone? All right. Let's continue. Okay. Oh, by the way, and next week we won't have class next week because I have a conference to attend a conference, so we'll have class next week. And on the 29th, I invited a director from Intel. I think he will visit Taiwan, and I invited him to this class. Okay, so I will post this on the class website, and he will talk about some scaling trend on the memory device. Okay, I think that was a very, very good talk for you. So the talk will begin from 10:30 in class. Okay, so before that we still have class. I will maybe take lectures one and a half hours, and then he will give lectures later. Okay, and the details flyers I will provide that later and post it on the website. It become open talk, so I will post it on maybe GSAT or ECE college to invite more students to join it. And I think it's a very good. He's a Taiwanese guy, so maybe he will. I don't know if he want to speak in English or Chinese. I haven't discovered it yet. Okay, but so you can get some latest information from Intel. Okay. Okay, so this figure show you that we have another inductively coupled IF antenna, which is on the side wall of your chamber. Okay, those inductively coupled plasma can help you to generate more ions. Okay, sometimes in the IE systems we only have one IF source to control the plasma. Okay, But here we may have another source to help you. You can control it independently. One is to generate more plasma. One is to control the DC. Like here we have a DC bias, so we can produce enough kinetic energy for your atoms. Okay. So by doing this, we can give a more focused direction of your ion. So that will give you this kind of deposition directions. Okay. That provides a narrow distribution of arrival angles. Okay. So if we want fill a very deep contact hole here, or make some metal to make sure it can go to a very deep hole, then we can use this kind of method. Okay, try to narrow the arrival angles, so it can go deeper. Okay, compared with this one, if you have different arrival angles, then you will have very good feeling of coating the bottom of this deep holes. Okay. Now, this is a important table that try to summarize the different deposition techniques. Okay. For the silicon film or polysilicon, we can use AP or LPCVD. So we have this kind of typical reactions formula here, and this is the temperature that we use. And for some dielectric silicon nitride or silicon oxide, okay, we can also use different CVD techniques. Okay, with this is the reactions. Okay, and the PCVD can have temperature less than 400 degrees. Okay, and for the aluminum, okay, you can use a sputter, you can use evaporations. It's very easy to process aluminum. Okay, for some titanium, tungsten, okay, you can use this LPCVD. Or of course we can use some sputtering also. And gold is like electroplating here. Okay, and this use sputtering deposition, or CVD. Okay. All right. So now let's move to these manufacturing methods. Okay. So they all summarize in this table, so we can move on quickly. For epitaxy, epitaxial silicon, because we need very good quality, okay, like a single crystal quality, then we can increase the temperatures, and we can use CVD or PCVD. Okay, but in some cases we use lower temperature, we can have amorphous or polycrystal. Okay, that's in some, because of some cost issues, then we can use some cheaper way to provide less this silicon with less quality. Okay. And this is polycrystal silicon. We can use a sputter or CVD with less restrictive condition than epi. Okay. So that's the TEM cross-section pictures of this CVD grown polysilicon. Okay, so this is doped thin grains in columns, and this is phosphorus dope with larger grains. And this one we anneal it. Okay, for this A, and this one we anneal it of this material B. Okay. So anneal that you can see this. You can have a grain. You begin to see some grain grain size to grow. Okay. And we can use this polysilicon because it can be used as a local interconnect, or a gate for your MOS capacitors. Okay. You see this resistivity here. And for nitride or oxide, okay, we use nitride oxide as a mask or a passivation layer. Okay, so we can use PCVD, LPCVD with these equations, okay, these chemical reactions. And silicon dioxide, we can use that as a isolation, okay, LPCVD or PCVD, and sometimes we use HDP CVD, high density plasma CVD. Okay, and for aluminum, okay, now in the more advanced technology node, okay, it has been replaced by coppers. Okay, we can use some DC magnetron sputtering. For titanium tungsten, okay, it's an underlay for contacts of vias between the interconnect layers. We can use sputtering. Okay. And for tungsten, okay, these tungsten plugs are often used, okay, to fill the via. So we can use CVD, like high wall and low pressures to do this. And also this the titanium tungsten silicide. And can you reduce the resistivity of polysilicon? Okay, with dope P regions and use sputtering or co-sputtering, co-evaporation of CVD. Okay. I don't think you need to memorize this, because once you go to the foundry, you know that usually there's other more advanced technology that you use. Okay, but this is true for some old technology node. Okay, so this is titanium nitride is a barrier layer in context, to reduce some diffusion issues. Okay, so it's pretty hard metal. Okay, so we can use a sputter or CVD. Okay, and copper, we use that to replace the aluminum because it has less electron migrations. We can use PVD for sputtering, evaporation, plating, okay, electrolysis deposition. Okay, electroplating, we can use to do that. Okay, now we quickly will do these methods. I say again, they don't need to memorize that, but for the model and simulations, okay, they can give you more insights of how it works for this for different deposition technologies. Okay, so we can use these figures to identify there are different kinds of fluxes, okay, during your depositions. Okay, so we have this direct flux neutron coming here, or direct flux, but this is ions coming. And we have this dissolved or emitted flux, okay, which means it come into one position and will emit to the other position. So this is a redeposited flux, okay, and we have some resputtered flux, and also surface diffusion flux. Okay, so net flux, we can just add all this into one equations. So we have some direct flux includes neutron and ions. and we have radiate one, okay, and also diffused one. So those are incoming flux, and for the outward flux is minus emitted or sputtered or diffused out. Okay, so when we try to simulate this deposition, we can try to find the mathematical description of each flux terms. Okay, and we can try to add it up, and we can estimate the growth rate or deposition rate. Okay, so we will go into one by one. Okay, let's look at this direct flux first. Okay. So for these direct fluxes, we can model it with an arrival angle distributions just above the wafers. So this is the gas phase. We can move around with different directions. So, and here this is the surface of the wafers, and we have different arrival angles, and it has a distribution at the plane just above the surface. So we can use this cosine theta term to model this F direct as a function of arrival angles. Okay, and this F direct is the normal component coming to these directions. Okay. And for the high pressure systems, we have more gas phase collisions and shorter mean-free paths, so N equals to 1. So in high pressure, it's more isotropic arrivals. So we have N equals to 1 dependence. But for low pressure systems, we have fewer gas collisions, so we have longer mean-free paths. So it's more directional. It's an isotropic arrival, so N is larger than 1. Okay, so for ionic species in the bias system, which means it has charge, and we provide a DC bias, okay, then it's directly arrival, okay, similar as this one, okay. So N larger than 1 is an isotropic arrival. So the N dependence can be seen from these figures. Okay, so N is equals to 15. So you see the angle distribution is less than 30 degrees. Most of the deposition coming within less than this 30 degree. And for N equals to 1, you can it goes to 90 degrees. Okay, so for at certain point I here, okay, there's a view angle. Okay, it depends on the surface topography. Okay, so previously here we know the incoming flux with different arrival angles, and it depends on the arrival angles. And now we need to consider the surface topography. Okay, so from certain point I here, there's a view angles. And this viewing angle and shadowing effects become important, and also the surface orientations. Okay. Okay, so for the indirect flux, this includes surface diffusion, emission, sputtering, and redepositions. Okay, and what is surface diffusions? If the surface, okay, again, it depends on the surface topographies. You have some local curvatures on the surface. Okay, so you can imagine that different local curvatures will give you the different surface free energies. So that creates these atoms try to move from high to low energies. Okay, So there's a diffusion in and out. Okay, diffusion in minus diffusion out is the diffusion net. Okay, which means that stays in the certain positions. Okay, so we have this constant, this omega and mu are constant, but we have this term. This is the curvature terms. Okay? So this diffusion difference, depends on these local curvatures. Okay. And this surface diffusion helps to fill in holes and produce a more planar depositions. Okay, because due to this surface energy difference, okay, they move from high energy to low energy, which means you try to smooth out the topographies. Okay, so that's the diffusion flux can help you to fill in the holes. Now we can take a look at these immediate terms. Okay. When we have these immediate terms, because not all molecules will stick when they arrive at their first surface. Okay, the first position at the surface. Like when you come to Taiwan, okay, you won't stay in Taoyuan. You probably will move around. Okay, that's sticking coefficients. When sticking coefficient high, you stay here. Sticking coefficient low means you like to travel around. So these immediate terms, we can consider that part of these incident terms. Okay, parts of incident terms can be moved and traveled or emitted to the other positions. So we have this 1 minus SC. Okay, so generally ions are assumed to stick, and neutrals, they can move around. And they were assumed to be emitted and with a cosine angle distributions. And this cosine angle distribution, emitting angle, has nothing to do with the arrival angles. So we assume there's no memory of the arrival angles. Coming from this direction, but when they emit, it can go to other directions. It has nothing to do with the arrival angles. Okay? And this emit term can result in a redeposition term. Okay, because we emit out and this is gonna redeposit on other position. You will land on somewhere else. Okay, so we have this redeposition, redip term coming from the re-emitted term. This one we just mentioned last page. Now we times the coefficient G here. Okay, this G accounts to the geometry between I and K. So K is the immediate position and I is the redeposit position. Okay. So this 1 minus SC times Fk is the F emitted. Okay, now we times 1 this G coefficient. So again, if this SC less than 1, we produce more conformal coverage. Okay, so this happens in the CVD. The CVD give you more conformal coverage because staking coefficient is less than 1. Okay. Now let's get into the Spartan term. So we have this Spartan flux. Okay, so it's primarily by this energetic incoming ions. Okay, so we have this argon, we have this direct deposit ions, and we have this Y we call it the Spartan yield. Okay, as we just mentioned before. And Y is angle sensitive. So from these pictures, you can see that around like 60, okay, 60 to like 70 degree, we have higher spartan yield here. Okay, so roughly around like 50 to 60, we have the largest edge rate because it's angle dependent. So you try to sputter your target. It's not like 90 degree or 0 degree because this is a surface. If you come in at 0 degrees, actually the sputter yield is pretty low. Okay, also 90 degrees, the same. So you come in like 60 degrees, so you get more sputtered out patterns. Okay. Okay, so those sputtered out molecules, now they're gonna travel and redeposit on your surface. Okay, so we have another redeep turn resulted from these sputter turns. Okay, so we have this Fk sputter times this Gik. Okay, so we have the same geometry coefficient here, Gik. Okay. And finally, we have one term, we call it ion enhanced or ion induced. So when we have ion striking on the surface, sometimes they can enhance the deposition rate. Okay. They can supply the energy to drive the chemical reactions. Because of the ion, it provides more energy, so it can give energy to the surface reactions. Okay, so this ion induced can we have a term called constant times this flux of this ion. Okay, so in this we have different coming flux. Okay, now there's a TCAT tool originally developed by Stanford University. But now this speed is worked by the Sivaco. So you use Sivaco, you basically use the same simulation tool. Okay. Now we understand that there are different fluxes. Okay. We already described all of them. Now we get into the different deposition system, and to see the different deposition system, what kind of terms should we consider? Okay, so the first one is LPCVD. We have these direct terms, ion or neutral terms. And there's no, okay, there's only neutral terms here, and no direct ion or diffusion term. It has emit and redeep one, but in the LP CVD they don't have sputter turns and no ion induced. Okay, so because you don't have plasma, okay, so you only have neutrals here. There's no ion involved and no sputtering, and your surface diffusion usually is not important here. Okay, so if you want to simulate the LPCVD, and okay, we can just need to add all the necessary terms in this net flux. So we have direct, we have redeep terms, okay, and minus this term, okay, this 1 minus SC. Okay, so but basically this term is the same as this in this parenthesis. Okay, so you write this, you can have this SC in front of this parenthesis, and we can write like this. Okay, so this direct and redeep terms we call it FD. Okay, this is deposition flux at each point. Okay, so now we have this rate equals to SC, and this is FD. and divided by your density. Okay. Now we also can consider this cosine theta terms to account for the incoming molecules with different angles. Okay, and for PECVD, we have an ion flux can enhance the deposition rate, and also we don't have sputtering, okay, because the ion energy is pretty low, so no direct deposition of iron is significant. Okay, so we just we generate this plasma. We have iron here, but energy is low, so no directly iron deposit. So we have only neutral here, and no diffusions. We have emit and reduced, no sputtering, but we have ion-induced terms. Okay, so the rate previously, this is the same as our LPCVD, but for PECVD, we just need to add this Fi term here. So this is correlates to this ion-induced. So you can see that the rate can be improved, can be enhanced by adding this term. Okay, so for PECVD, we can give it at a certain temperature, we can increase the deposition rate. Okay, or we can maintain the same deposition rate at lower temperatures. Okay. Okay. CVD, PVD. All right. Maybe we can stop here. Okay, we can come to this next time, but we will have class next week. Just for your reference, I will announce it on the class website. Okay.